Good afternoon to everyone. So I'm going to talk about the mechanical behavior of the az31b implant biaxial fatigue. These are the authors of this work. And first let me present you our institute in Lisbon. So this is the main central building, our campus, and here on the left we have the mechanical engineering department. Moving now for the outline of my presentation, here we have the topics, so I'll make a brief introduction and the motivation of this work, and then define the objective, I'll present the material, the equipment, and the methodology, and then I will talk a little bit just about the critical outline models, I'll present the results, and I will conclude with some remarks. So, well, I don't know if you are, all of you, familiar with this topic. Why we study biaxial fatigue or multi-axial fatigue, because we have in the real world several structures and components running under multi-axial stress states. So we have to study this phenomenon. And here we have two different cases. Well, gunshot that was in bending and torsion, and also the well-known airline flight accident in 1988, where we have biaxial dislocation example. So we are interested in this. Just to call your attention for these mechanisms that are very important in the biaxial loading class. So the microstructure of the different materials has a corresponding effect on the mechanical behavior of materials. So we are interested today to study the magnesium alloy. And I should also call your attention for the proportionality and non-proportionality of the loading path, which has also influence corresponding to the taking into account the different microstructures. So, as in case of the non-proportional one has presented here, in case of the alternating stainless steel, we have an increasing this sensitive material to non-proportional loadings. Another example is in this case, the movie is not working, but if I apply different components, here I have the axial one, and here I have the torsional one. In different cases, I have the same final loading path, and of course, now it's working, I have different fatigue lags. So, another important aspect in multi-axial fatigue or biaxial fatigue is the sequence effects in the loading lag. Then, why magnesium alloys? So, as you can see, there are two main industries, aeronautic and automotive industries, where we have successful industrial applications. It's the sixth most abundant metal on Earth, and also because we have it's an advantage due to the high specific strength of this material. So now let me show just briefly some work already performed by our group in Lisbon. So now corresponding to the planes specimens and concerning the isocratic test, we have performed this test, and we have some data corresponding to growth and fracture morphology. And also with small notches here, we have performed some tests, and we are analyzing the influence of the notch in crack growth. Depending also on the crack of the loading path, we obtain different morphologies. Concerning now the LCF tests, well, we have also made some examples, some tests, as you can see here, in pure torsion and in pure tension compression. And we observed that we have different behaviors. We can have a kind of asymmetric behavior in the case of pure tension. So this is called orientation. And after that, we have also performed more cases, and then we propose a cycloelastic plastic model just to take into account this asymmetric behavior of this alloy, and we propose a cubic polynomial to fit this behavior, which is already published this model. Now, bringing us to the topic, we are interested to know all the mechanical behavior of this alloy in the 4 planets, and well, we are going to perform some tests here and here in the biaxial plane. So the objective of our work is to evaluate mechanical behavior and namely identify experimental initial crack orientation planning under the defined loading paths in relating with the estimated length. We also want to establish the ADN and delta K relationship for the carried out conditions, and also to evaluate the fractal surface morphology after performing the carried out experimental tests. So our machine, being playing biaxial testing machine with 4 linear independent engines with a dynamic capacity around plus minus 3.5 newtons, a maximum displacement 85 millimeters. The maximum frequency in uniaxial we can achieve 100 Hz, and in the case of biaxial we achieve 20 Hz. Then we have used USB microscope just to monitor and to detect the correct initiation. So we can make a film, we can take some snapshots along the test, and then we can take into account the number of cracks and how cracks forms and how they behave and so on. Here the material, so the main properties, mechanical properties, the composition of the material, as you can see here, and here the end models around 45 gigaton, and here the main monotonic mechanical properties, the tensile strength and the yield strength around these values. Moving to the biaxial specimen, so we have used this geometry for the cruciform specimen. So here we have 200 millimeters, also here, and this shape is very important because we need to ensure that the maximum stresses occur here in the center. So here we have a radius of 7.5 millimeters, and we also take into account the direction, the rolling direction of the material. So this is direction longitudinal was chosen by the inside with the rolling direction, and here we have direction to the transversal line. Well, we should take into account that we should optimize this specimen to make sure that we have here a low stress concentration and also, let's say, a constant field of stress here. So because we want to ensure that the failure occurs here in the center of the specimen here. So we have 0.364 millimeters here, and the thickness of the specimen is 3.25 millimeters. We have published last year, on the biofracture mechanics, let's say optimization procedure. If we change the thickness of the material or the thickness of the width, we just have to be very careful because if not, we can grow specimen here or here or here. So this should be very careful. We should read this paper to optimize your specimen. So we have performed also the finite element analysis to ensure that we have the maximum stresses here in the center of the specimen. And to manufacture the specimen, we have followed 3 stages. The first one is to cut with a pseudo-abrasive water jet the specimen. Then the specimen was machined in a stencil to obtain this. And after the third stage was polished by hand here in the middle just to achieve a good finishing. Well, these are the conditions where we performed our tests: not control, temperature, constant amplitude, equal loads in both directions, and the stress ratio, frequency, and well, I'm going to show you now the loadings that we have performed. So these are in phase. So we have performed till now. This is an ongoing work. So till now we have performed only 6 tests. But some of them are not so good. That's okay. So 3 in delta is equal 0. It means we are in phase. The other ones are out of phase. Don't be confused with the low proportional. All these loading paths are proportional ones. So we have here 45 degrees, 90 degrees, and 180 degrees. Okay, so well, as you want to achieve also the law, the equation of the ADN delta K, so we need to achieve, to take into account K1 and K2. So we have used this proposal by Richard Center, and in this way we can take into account the equivalent, stress intensity factor equivalent, and we have modeled the specimen and the crack. Based it. So after performing the tests, which we have monitored the crack initiation and propagation. So we can monitor, we can design our crack, the orientation, of course, apply the boundary conditions, the loading conditions, and in this way we can achieve the stress intensity effect. Okay? So these are the elements, the number of elements, the type of elements that we have used, and the number of nodes. Well, moving now for the critical open models, well, I'm just putting here some of the used ones. These kind of models allow us to identify the initial crack orientation. So depending on the variables that the damage parameter takes into account, they help us to identify the critical points. So let me show just briefly with Finlay criterion. In this case of the shift angle of 90 degrees, we have obtained this, the loading path, and these two are the critical points for this loading path. Now moving, just last example for titanium cells, for instance, in the case of the loading 180 degrees, so we are talking about this loading path. In this case, we have 4 critical points, as you can see here. Okay, so we identify here the loading path. We have sweeping from minus 90 degrees to 90 degrees, and we identify here the damage parameter, and that's on parallel. So this for critical points appears here, minus and plus 55, so as you can see here, so we are here around here, 55, okay, moving on. Well, we obtain this, all this data. So these ones are the critical points for the different critical plan criteria, and we have made all 4 out-of-phase loadings, are the results appear here. Here I present the experiments, so the obtained results for the after the experiments we have identified, because we can monitor the crack growth, and we obtain this. And as you can see, well, the astigmatism bottom topper and the new one, which is based on the work, based on the normal work, let's say, optimization of this parameter. So we have identified here the normal strength, principal normal strength, allow us to better correlation with the experiment. Now, moving for the crack propagation. So, as you can identify and you can measure the crack growth for certain intervals, we have take a snapshot of the crack growth and we identify. So here we have obtained the crack length, and here we have the number of cycles. We have performed this for all specimens, not so much till now, but here for the other specimen shift of 45 degrees, you can see here number of cycles around 46,000 cycles. Here we identify, well, you cannot see some conditions, but we have here a crack, another one. We also performed for a shift angle of 90 degrees, so we have here from 0.2 millimeters and until about 600,000 cycles, almost there. And finally, we have here the delta equal 180 degrees. So we have also performed tests. This means we have this one in tension, this one in compression, and we obtain also the crack growth, so the number of cycles versus the delta. Well, till now we have plotted here all the data that I have achieved, and well, we can say an average trend of all this data. And I have here the values. Of course, this is an ongoing work, so we have to perform more data, but till now. And also here, take into account the fracture surface of the morphology of the specimens after the test. So, well, as you can see here, well, there's another branch here, another branch. And here, well, these two means that we are in the presence of different loading paths, and there's an evidence of this effect as we are concerning one loading path or another one. So, okay, these are final remarks. I think I have already said it's here, and I have to finish. I have to thank the Portuguese Foundation for Science and Technology for their support, and I will thank you for your kind attention.